Hello.
Sir, am I audible?
Yeah. You are
Yes,
audible.
yes, sir. Yeah,
Yeah.
we can see you.
Okay. Yeah.
So we'll start in 2 minutes only, so that
Yeah. Sure.
most of
Sure.
the participants will. Okay, I believe most of the participants have joined.
Mhm.
So that okay, so participants, we'll start the session. Uh, so we welcome Dr. Lalitkumar Singh. I'm giving a brief introduction. Dr. Lalitkumar Singh has done his PhD from IIT BHU, Indian Institute of Technology, Banaras Hindu University, and currently Sir is scientist and head of artificial intelligence applications at NPCIL BARC, that is Department of Atomic Energy, Government of India. Sir has a distinction of working on a number of several very challenging topics, challenging jobs, including working on pressurized heavy water reactors, light water reactors, ranging from design, development, testing, and many more. Sir has a number of publications in IEEE transactions, IEEE computer societies, and many more. Sir is a senior member of IEEE and achieved multiple awards, including the very prestigious IEEE K. Shankar Award for publications, group achievements, etc. Sir is a founder member of industrial and an industrial coordinator of Center of Dependability IIT BHU, which is proposed. Sir has been reviewing multiple publications, also a part of advisory board BOS of many universities. And Sir is also working as a faculty of Nuclear Training Center at Department of Atomic Energy, Government of India. So we have been attending sessions day 1, day 2, day 3, and today we are in on the day 4, and we are very lucky to have Dr. Lalitkumar Singh, and we are I hope hopeful that it will be a very nice, very informative session. So please be patient and attain the full session. You can ask any question if you want in the chat box. So sir will be able to answer maybe in the end of the session. So sir, we can start.
Okay. So, am I audible?
Yes, sir.
Yeah. Okay. So, very thank you uh, for the introduction and for inviting me for this talk to share some of the experiences to all the participants. So, welcome all the participants. Okay, so let me start my session. So is my screen visible to all? Are you able to see the slides?
Yes, sir.
Yeah,
First slide.
okay. Yeah. Okay, so I'll be talking on reliability analysis of communication protocol for safety critical systems. So first, let us try to understand the meaning of this topic, what actually this topic means. So the the first, the reliability. So reliability, you all know, in you know here and there we use this term very frequently, like you are not reliable, or this is not reliable, this system is not reliable, like that. But actually, what reliability means, if you talk in the terms of precise definition, it is the probability of failure free operation of the system up to a given period of time and under certain environmental conditions. So this definition is very important. As I said, it is a probability. So we know, like, probability ranges from 0 to 1. 0 means less reliable, 1 means highest reliable. Okay. And of failure free operation. Failure free means success operation up up to the given period of time. Now here the time is very important. Up to what period of time we are talking about anybody's reliability, because nothing is reliable for the infinite period of time. So you have to explicitly express up to the given period of time. And then under certain environmental conditions. Now, under certain environmental condition, that is very important, because reliability always depends on the environmental conditions. For example, suppose you purchase a refrigerator and you get a warranty period of 1 year. Then you come back taking it home to your home, and suppose you throw it from the 10th story, then it will collapse and you cannot go to the vendor and ask, like, you have given the warranty period of 1 year, so I want the replacement. What he will say, no, the warranty has been voided because you have not met the operating conditions. So what I wanted to emphasize from this reliability definition, it depends on the time, up to what period of time you're talking about, and it also depends on the environmental condition. So I'll be discussing the reliability quantification of the communication protocol, like all, like protocols, communication protocols in which we can, connect with the devices. And for safety critical systems. Now, safety critical systems, this is a very important term. So these are the systems, the failure of which can lead to the catastrophic disasters. For example, aerospace, nuclear, or defense, medical, where the safety is very important, and the failure of such systems can even lead to the loss of human life. Okay. So, okay. So this is a quick agenda of today's session. So first, the introduction to the reliability and background. This I have already discussed. So but we can see, like, how mathematically we can define the reliability. The second one, next we will understand the Petri nets and modeling of the systems. So Petri net is a mathematical modeling technique. The concept was introduced by Petri, C.A. Petri, who was a German PhD scholar, and he basically introduced this mathematical formalism to capture the stochastic behavior of the system. So if I talk about or the stochastic process. So if I talk about the process broadly, it can be categorized into two. One is the stochastic process, and the second one is the deterministic process. So the deterministic process are those processes, the output of which are 100% guaranteed. Suppose I do have a pen in my hand, and if I drop it down, I can 100% guarantee it is going to fall down on the earth. Why? Because of the gravitational force that is acting on it. So, but the stochastic process, these are the random processes, and whose output cannot be 100% guaranteed. For example, suppose I'm here, to deliver my talk, but it could be possible that I could fail to deliver the talk because of maybe some important meeting got in line in my office, or maybe some other important assignments, or some unavoidable circumstances. It can always happen. So what I mean to say is, even after rigorous planning, it is possible, like we may fail to give the desired output. And such processes are known as stochastic processes. And even human is stochastic in nature. So all the derived, systems of the human are definitely stochastic in nature. So we will see what is the working mechanism of the Petri nets, what are the basic building blocks, and then we will also see what are the important properties of the Petri nets, what are the analysis techniques, and then I will be introducing the reliability prediction framework, in which I'll be discussing some of the important phases that we need to uh, implement, and that will lead to the quantification of the reliability. Then we can conclude our session. Okay, so now let us see the mathematical definition. So suppose let x be the random variable representing the time to failure of a component. It means this much time that my component is going to take to fail. Then the reliability of the component at time t will be given is by P. P is what? It is a probability. So because I'm talking about the reliability, it means this X, which represents the time to failure, it will always be greater than the target time. Means it should not fail before the target time. Then I can say this is the reliable, right? So this equation is very clear. And from the total probability law, we can equate it is equal to 1 minus P, x is less than or equal to t. It means it is now failed before the target time. So it is nothing but it is a failure probability, which we can write it down is equal to 1 minus failure probability. That is fxt, just to denote it. Okay. So now let us discuss some of the traditional methods through which we can quantify the reliability. So the first is reliability block diagram. So in the reliability block diagram, what happens basically, any system we decompose into subsystems or at the component level, and then we can find out how those components are arranged, whether in series or in parallel. And if I know the component reliability, then I can find out the overall system reliability by series or parallel reliability formula. For example, if my system, or if there is a system which contains only two components having reliability R1 and R2 respectively, and they are arranged in series, so the overall system reliability will be R1 into R2. Okay. So in that way, if they are arranged in parallel, I can use the parallel reliability formula. Okay. Similarly, there is one more construct, that is the reliability graph. And because it is a graph, we know graph contains nodes and arc. And nodes are used to model the link between two components, and arc basically represent the component itself. So if you see this figure, the left figure is reliability graph, where all the vertices like A, B, C, D, these vertices are representing the connectors between the components V1, V2, V3, V4, and V5. These are the components because arc represents the component. And it can be equivalently transformed into the reliability block diagram. So if you see the figure in the right hand side, it is a reliability block diagram. where all the V's are basically components have numbered from 1 to 5, and all the vertices are basically representing the arc, which are connectors of the components, right? So, and now you can see like 1 and 4 is in series, 2 and 5 is in series, and then this three segment will be in parallel. So you can use the series and parallel reliability formula to compute the reliability of the overall system. Okay, there is a one more very prominent method for the reliability prediction or estimation, that is known as fault tree. And fault tree is a basically deductive approach. And we know like tree has a root and branches, so it is like root and branches. The top level component is known as a root. And in this approach, basically we try to deduce the cause of the failure. For example, here you can see the car will not start. Now, what could be the reason? Suppose some control system has failed or some electric fault has occurred so that like your battery is not starting and so on. So there is a OR gate. So it means if any of this event happens or occurs, your car will not start. Similarly, for the control, what could be the things? For example, it is already my parking mode is on. Okay, so when I have switch on the parking mode button in my car, it will not start because first I have to switch off the parking mode. If I do have, I have applied foot on the brake, it will not start like that. So there could be multiple reasons, multiple bases, the cruxes you have to deduce till you reach to the very basic level. And then if you are able to find out the failure probability of these basic events, for example, in this figure, the basic events are in park, foot on brake, starter faulty, broken wire. So the probability of the failure, if you are able to assign, and if they are arranged in AND logic, then you have to multiply that probability of failure to uh, you know quantify the probability of the top event. For example, if in park has a probability of failure P1, foot on brake is P2, then control status will have a probability of failure will be P1 into P2. And similarly, if they are arranged in the OR logic, then P1 plus P2. And in that way, we can keep on propagating towards the root, which will find out the probability of the failure of the car will not start. And to know the reliability, I have to subtract it by 1 because it is a probability. And we have already seen 1 minus probability failure is a reliability. Okay, so now the models that we have looked so far, these are the state space models or deterministic models in which it is very much essential that you should have some prior information about the failure rate or failure probability of the components. But the systems are always dynamic in nature, which keeps on changing their states with time. And hence, there should be some mechanism which should be able to capture,
ડોક્ટર કહી શકતો આમાં નથી બતાવતું મીટિંગમાં કેમ નથી બતાવતું
which should be able to capture the dynamics of the system. Okay, I request you all of you to please mute yourself so that the other participants should not get disturbed. Yeah. Okay, so to capture the dynamics, like there are many other models For example, there is a Markov model, which is a very powerful model, and which was introduced by Andrew Markov in 1940s, who was a Russian mathematician. And he introduced this Markov model, uh, keeping in a view like any system can be decomposed into the various states. And uh, one system can transit from one state to another state. For example, if there is a human being, it is a system. There could be multiple states of the human, like walking, talking, eating, running, sitting. So some states could be the normal state and some states could be the failure state. For example, meeting an accident is a failure state. So generally the normal states are known as behavioral states. Okay. So if somehow I'm able to find out the probability of the system being in all these states, I can add all the probabilities of the success states and that will give me the reliability. The other way out is I can add all the state probabilities of failure state probabilities, and then I can subtract by one. That will give my reliability. Okay. So let us now understand some of the mathematics or preliminary mathematics which we will be using to quantify the reliability. So suppose there are the two states, my Markov chain, you know, containing many states, and suppose there are the two states I and j, which belong to S. S is the total state space of the system. And let Qij be the transition rate from state I to j. Transition rate means number of transitions per unit time. It is a transition rate. And then I can calculate the self transition rate, that is QII means it is transiting from I state to I state. It will be is equal to minus, you have to sum all the transition rates except the self transition rate. Okay, so minus Q summation all ij's, where j will not be equal to I. Okay. Uh, Fine. Then I need to define one terminology, that is the generator matrix, and which is defined by Q. It is nothing because it is a matrix. It contains rows and columns, and each element basically represent the transition rate of different states from one state to another state. So we'll see more insight about the transition rate when we'll be discussing the real case study. Okay, now coming to the PatriNet, as I have already told, like PatriNet, it is a mathematical formalism and which is a very good graphical and mathematical tool. Why graphical tool? Because I can simulate, uh, I can model the real system and I can then run that model so that I'll be able to see the behavior of the system in the graphical format. And why it is a mathematical tool? Because I can embed the mathematical knowledge and to know more and more insights about that particular system. So we will see like how it will be it can be used as a graphical and mathematical knowledge and mathematical tool. Anyway, we will be using the mathematics to quantify the reliability of the entire system. So it is a concurrent, it can be used for concurrent, distributed, asynchronous, any kind of system. So it is the best communication between theoreticians and practitioners. So if you look into the history of the Petrinet, starting from its origination to some of the important milestones. So, as I said, it was introduced in 1962 by C.A. Petri in his dissertation, who was a PhD, Germany PhD scholar. And after after going through his thesis, the people were started taking interest. Like, this model has a capability to model the concurrent systems or parallel computation, because that was the time where the people was striving for parallel computation and concurrencies and all. So with this, MIT USA conducted a project, or conducted a conference on concurrent systems and parallel computation, to know like how this PatriNet can be used for to model these kind of systems. And the conclusions were very fruitful. So again, they decided to meet after 5 years, uh, to talk more about what could be the uh, initiatives, or what could be how the models can be strengthened. And then after it got so much popularity that the courses started coming up. And the first course on general net theory of processes and systems was conducted in Germany in 1979. And people from the other domain also started taking interest whether this net will be able to model their specific kind of systems. And with this objective, again, a France conducted the first European workshop on applications and theory of battery nets. And then people researchers started coming out with more flavors of PetriNet. For example, if they want to model the real-time system, so definitely the PetriNet should have the timing information. And such kind of PetriNet they termed as timed PetriNets. So the first international workshop on timed PetriNet was conducted in Italy. And there are other flavors of Petrinet as well. So although this is not an exhaustive list, but it gives the origination of Petrinet, and along with the important milestones. And okay, so if you look into the working mechanism of the Petrinets, so suppose, let us take an example. I want to model a very, very small chemical reaction, that is 2H2 plus O2, that gives two molecules of water. So now let us see how we can model this chemical reaction using a Petrinet. So if you are able to see this figure is a Petrinet figure. And first let me make you understand what are the basic building blocks of this Petrinet. So then we will, see the working mechanism of the Petrinet. So if we are able to see the big circle, so there are the three big circles in this Petrinet, and I'm using one to represent oxygen, the second one to represent hydrogen. So this is first is hydrogen, second is oxygen, and the third I have used to represent the water. And okay, after that, you would be able to see a rectangular box that is known as transition. So any place can be connected to transition or vice versa, but there can be no direct connection between the places and between the transitions. And they are connected with the help of directed arc, weighted and directed arc. Why weighted? Because it contains a weight. So if you are able to see, there is the transition from hydrogen place to transition T contains the weight 2. But interestingly, you could have observed there is no weight assigned uh, in the arc that is connecting your oxygen place and transition, T transition. So if you don't put any number, by default it is treated as 1. So the weight is 1. We will see what is the significance of this weight in a while. Uh, but okay, now you are able to see the small embedded circles that are the solid circles inside the places. And for example, the hydrogen contains the two solid circles, and they are known as tokens. So here I am representing tokens means number of atoms in the hydrogen. I am representing, I'm using token to represent this. Similarly, oxygen is also a diatomic in nature, and hence it also contains two number of tokens. And interestingly, the distribution of the tokens among all the places represent the state of the system. For example, here the two tokens are in hydrogen, two are in oxygen, and zero in water. So 2, 2, 0 represents the state of the system. Now, whenever so this in this equation, you are able to see the 2H2 plus O2. This is a left side model. This petri net represents the left side of it, and now it has to convert into the water. It means it needs to change its state. And by law, any petri net can change its state only if all the input places must, if any transition is in the enabled state, okay, then only it can change the state. Now, but what there is an enabling criteria of transition, which is that all its input places must contain sufficient number of tokens. So because it is a transition T and all its input places, that is hydrogen and oxygen, must contain sufficient number of tokens. So hydrogen must contain 2, and who will decide the sufficiency of the token? The weight of the respective arc will decide. So here the significance of the weight comes in. So because here the weight is 2, so the hydrogen place must contain 2 number of tokens, and the transition connecting oxygen place and transition T, this arc is having weight 1, so oxygen must contain at least 1 number of token. And this condition satisfies, and hence this transition T is enabled state. Okay, so when this is enabled state is means now it can change the state, and because it fulfills the criteria, and to change the state there will be the movement of the tokens from input places to output place. But how many number of the tokens will move out from input and how many will deposited into output, that again will be totally governed by the weight of the respective arc. So here when this transition, the enabled transition, it automatically fires. So when it will fire, the two tokens will be moved out from hydrogen place, and one token will be moved out from oxygen place. And how many will be deposited into the water? Only two places will be deposited because the weight of the output arc is 2 only. Okay, so you can see the next state is this, which is the water state. So 2 tokens have been removed out from the hydrogen and 1 token has been removed out from oxygen. and 2 token has been deposited into the water. And now, can you observe? Now, still your transition T is in enabled state? No, it is not in enabled state because what was the condition? The condition was all the input places must contain sufficient number of tokens. So if you see in this figure, the hydrogen place is not containing any token. So, but it must contain at least 2 number of tokens because the weight of the arc is 2. Although oxygen meets the criteria, place because it contains 1 token and the weight of the arc is 1. But I said all the input places must contain. So hydrogen should have also contained sufficient number of tokens. And hence now it is not in enabled state, so it cannot change the state. Okay, so now the state is, because I said the distribution of the tokens represent the state. So 0, 1, 2. So earlier the state was 2, 2, 0, and now it has been changed after firing transition T, 0, 1, 2. Okay, so it means, uh, you know, I want to now introduce one interesting terminology, that is reachability graph. So basically reachability graph, as I said, it contains node, what is graph? Which contains nodes and arc. So reachability graph basically tells how many total number of states are possible in a system throughout its lifetime. So the node will represent the state and arc will represent the transition because one state can transit to the another state, and it will go through, it will identify like how many total number of states are possible at all. Okay, so anyway, that was the concept or the working principle of the battery net. Now coming to the Markov chain, I have already discussed a little bit about the Markov chain because as I said, this concept was introduced by Andrew Markov in 1940s to you know represent the state space of the system. I mean, it contains the states and the transitions. So basically, the crux is you can decompose any system into the various states and how it is transiting from one state to another. So if you see the mathematically, and one more property of the Markov chain is the next state will only depend on the current state and not on the previous states. That is but obvious. It is based on the practical life. So how like mathematically we can represent this property? So suppose there are the sequence of random variables, x1, x2, and so on. Then what Markov property says, like probability that my system is in n plus 1 state is x, then it will only depend on what is the probability that my system was in nth state and not on x previous state. So hence all the previous states has been deleted or discarded, and it is only depending on the you know current state. Next state will only depend on the current state. And pictorially, I can represent this Markov chain like this, as shown in the figure. Suppose your system contains only 2 states, S1 and S2, and how it can transit from S1 to S2 and S2 to S1 like. Okay, this is a random slide. It is just to make you understand what is actually the reachability graph and how it is represented. So the left figure, this is the reachability graph. And as I said, this graph contains node and arc, and node represent the states. And if you are able to recall, I told you the states are nothing but it represents the distribution of the tokens among the places. So if you are able to see, this is the state having 1001010. It means I'm assuming that there are the total three, four, five, six, sorry, seven places, and in one place there is one token, in the second place there is zero token, and like that. And maybe T1 may be in enabled state in that figure, and if it fires, it changes the state like that. So this is nothing but it's a token distribution. So this is just random slide. I have not, taken any particular PatriNet model to derive this reachability graph, but I just wanted to show how the reachability graph can be derived, which can further, lead to the derivation of Markov chain. So what we have already seen, what do you understand by Markov chain? It contains the states and the transitions between the state. So this is a state, all the M1, M2, M3, these are the states. So I have represented the state by circle as being represented in the Markov chain. So this is just equivalent. I have transformed the reachability graph into the Markov chain. So all the states I have termed, I have represented by circle and named at 1, 2, 3, 4, and 1 to 2 there is a transition lambda 1 which represent the transition rates from one state 1 to state 2. Lambda 2 is the transition rate from state 2 to 4, like that. Okay. So just to show how it can be represented, because we are going to use in our framework. Okay, now I have discussed some of the fundamental concepts which are required to understand the framework, all the framework activities, the reliability prediction framework activities, and now, let me explain the reliability prediction framework. So generally, it contains the three phases. And in the first phase, you have to create the PatriNet model. And that we have already seen how we can create the PatriNet model. It contains, the places and the arcs and transitions, and places and transitions are connected by the weighted and directed arcs. So first we have to understand the system specification and create a PatriNet model. Next, we have to convert this PatriNet model into the Markov chain, and that also we have discussed, because we know, like, from the PatriNet model we can create the reachability graph, and reachability graph can be converted into the Markov chain that we have already seen in the random slide. And then the reliability can be computed by using the mathematical knowledge, which actually we will see how we can do that. Okay. Okay, so before coming to the real case study, let me uh, make you aware of uh, one more important concept. So, mathematical concept. So, suppose there is a pi IT which represent the probability that a system is in state I at time t, where I represents all the failure states and or behavioral states. So I could be any state, either failure or behavior. So assuming there are M failure states and then behavioral states, I have written like that. So as t goes to infinity, all these probabilities converges to a stationary distribution. Now this is a very important concept, which says that uh, any system, can be settled down within, in infinite period of time. So for example, let me explain with the help of very small example. Suppose you do have a glass and you filled it with water and put it down. You will see like initially your water will be in very zigzag mode, and after some time it is settled, it is completely settled. Now, suppose in place of the glass, you take the very big container and fill it with water and lift it up and just put it down. What you will see? It will take a very, very long time to settle down as compared to what was taken in the case of glass, right? So the crux is, if your system is complex, it will take more time to settle down. But yes, definitely, like theoretically, if I assume that the time is infinite, then any complex system can be, settled down, or can also all these probabilities can converge to the stationary distribution. Okay? Then, so the steady state probability is represented by pi, and that uh, arrow, title arrow, is equal to pi, all the failure states and behavioral states. And now which can be computed by the two equations, and these two equations are very important. The first equation is very simple. It just says like the probabilities, the all the of all the state that my system is in that state, or in all the states will always be equal to 1. That is a total probability law also. Now the second equation is very important and very, interesting to understand. So suppose, recall, just I was giving you the example of water, huge amount of water in the very big container. When I put it down, it was settling down, and suppose, initially, uh, a very initial point, the state is S0, and suppose after delta t time, it is propagating towards settling. So let that state is S1. Then this S1 will always depend on S0 into the transition probability from S0 to S1. That is, because it is transiting from S0. And now coming further down, suppose the next state is S2. After S1 state, it is again trying to more and more trying to settle down. And then S2 will always depend on S1 into the transition probability from S1 to S2, and so on. Now, there will be a time where your water has completely settled down. Let this state is known as Sn. So now the the next state will be Sn plus 1, and that will be is equal to, Sn again into the transition probability from Sn to Sn plus 1. But Sn plus 1, it will remain the Sn only because it has already been settled down. So the next state will always be the settling state, the same state, and that is what this equation represents. That is, it is a steady state, it will remain in the steady state into the transition probability. And because, you are considering multiple states in a system, so it will be a transition probability matrix, the matrix of all the states. Okay. Okay, now let us try to understand the communication module. Okay, so just leave this. It's not much related to that. Uh, but suppose there is a one network, and you are having the. Uh, Let me explain this network. What is actually? You are having the embedded unit, which is capturing the data from the field sensors. Field sensors, like it may be telling what is the tank level, or what is the uh, like status of valve, it is open or it is closed, and so on. What is the pressure of particular pipe, and so on. And because these signals are transferred in terms of voltage, which gets converted into engineering unit, and now this data needs to be transferred to the display unit, because there is an operator and he wants to see that data in visual formats. For example, either tabular trend or tabular format, or graphical format, and so on, or bar graph, whatever. So it means the embedded unit needs to transfer the data to this display unit, and it is transferring the data from the LAN, that is a lateral network. Now you could see I have taken the two embedded units because of the reliability, because if one fails, the another one should be uh, taken over. He should take over. And similarly, there are the two display units, so that in case of failure of one, the another can take over. Similarly, there are the two LANs, so that if one communication network fails, the other communication network will take over. Okay. And now I need to model uh, this basically protocol. So this is a kind of protocol. So the protocol is very simple. Okay. So suppose, I want to talk to my friend through a phone. I lift up a phone, I dial the number, and I say hello. Once he picks up the phone, and then I will start waiting for his acknowledgement. And once I listen his acknowledgement, I assume like the connection has been established and we can start conversation. It is a normal practice that we do. Mm. Now, suppose um, if I'm connecting the friend and I'm saying hello, hello, I'm not getting any response from the other side. What does it mean? It means there is definitely, I mean, uh, connection loss, and I can cut the call and I can again, retry. Okay. And so the same philosophy has been followed here. So whenever the embedded unit sends a new packet, the value I have kept one variable count, and I will set it to 1, and just to represent or to denote that it has sent a new packet, and it will wait for the acknowledgement for T1 after sending the packet. So because it has to wait for the acknowledgement. Okay. And now if embedded unit receives acknowledgement before T1, packet send is successful. And I have kept one flag, you can say like semaphore flag, or whatever, is changed to its complement. Okay. So I'm just putting a flag. For example, if some work is going on the road, I'm just putting it up, and if uh, uh, the work is not going, I'm just putting it down like that. So if the number of count, because how many times I need to say hello, 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 right? So I have to predefine it. For example, if I permit n number of times, so if the count is less than n, and if acknowledgement not being received, then I can say hello, hello. So it means the embedded unit will keep on retransmitting the packet, and it will set the value of the count. It will keep on incrementing the count variable, so that it can come to know how many times it has attempted to send the packet. Otherwise, embedded unit will terminate, and terminates the send process unsuccessfully, where the semaphore variable will not be changed or the flag value will not change. Now I need to model uh, this communication protocol using the battery net. So it is very easy to model. So this is the model basically. I will explain uh, everything about this model. But here interesting thing is all the arcs are having weight 1 because I have not put any number. So by default it is treating 1, and so all the arcs are having weight 1. So if you are able to see uh, this figure, there are the initially at very initial time there only two places contains the tokens. One place is PSRDY0. So it is known as what actually this place is represents, that embedded unit is ready to send the packet with some sequence number. And PDSR also, sorry, PDSR also uh, containing this. I'm in a meeting. मैं मीटिंग में हूँ, मैं करूँगा थोड़ी देर में. मैं मीटिंग में हूँ. Okay. So PDSR, sorry, I got a call. So PDSR, it represents the embedded unit gets request from the display unit to send the data. And if it is ready to send the data, and if it is getting the request, then definitely it will send the data. And what this S0 represent, that embedded unit sends the packet with the sequence number 0, and after sending it will increment the count value 1. It will set the value of the count. And PSW0, it represent the embedded unit is waiting for the acknowledgement. For what? Which packet? For sequence number 0. Whatever the packet they have sent, for that he is waiting. And then TSW0. So I mean to say, like, if the token will deposit in PWS0, then it will signify that embedded unit is waiting for acknowledgement with sequence 0. And TSW0, this transition represent that embedded unit detects the timeout of the acknowledgement. It means hello, 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 I have said a lot of times, but then also uh, it's not responding and it is timeout. And then the timeout signal will be representing by depositing the token in PT0 and 0. Okay. And after that, this TS0K, it will represent like embedded unit sends the packet, uh, and it will fire only when the total number of times the packet needs to be sent has not been exhausted. So this loop will keep on continuing till that. And if there is everything is okay, so the data packet will be sent, and this transition will fire. That is it represents like the display unit sends the acknowledgement to embedded unit with sequence 0. And then the data token will be depositing in PR1R place, which will represent that acknowledgement with sequence number 0 has received. And because the acknowledgement has been received, and so the wait for the acknowledgement will be over. So this transition will fire. So all the input places, it will contain one token that will be moved out. And again, it will be reading. And one token will be deposited here, one will be deposited here. And one interesting thing you can see, like, it is just symmetric in nature. So why symmetric? I'm trying to send the packet from uh, the embedded from the alternate embedded units at the alternate time. This is a very important concept, and it ensures the online testability so that I can keep on uh, having a confidence like, okay, it is working throughout their embedded unit and all the communication. But if your data or has not been sent, and all the time has been elapsed or the number of attempts has been elapsed, then this transition will fire, that is TS0 ACK unsuccessful. And with from this, the token will be deposited into this place, which is known as that send data unsuccessful, and which is reported to the operator. So this is the complete model of my specification. So the crux is, whenever you have designed or defined in the specification, you have to model it uh, through the battery net. And this we have seen how this communication protocol has been modeled using this battery net. Now, so after creating the battery net, we have to assign the delay of every transition. See, all these are the transitions, and that delay can be assigned from the statistical inference. For the similar kind of projects, you can see like, okay, how much delay was there for each transitions, and you can use the statistical techniques, averaging out or making the use of artificial intelligence to predict, the transition rate based on this experience, and the improved delay of each transition. So with that, we have inputted the transition delays as this is 0.001 second and so on. And after putting, all the transition delays, you have to just run. Uh, there are the various tools that are available in the market like TimeNet, Battery, and here we have used TimeNet. So if you will run, which is an open source, that will give the throughput of all the transitions. And what actually throughput means? Number of transitions per unit time. Okay, so all the throughput values will be calculated for each of the transitions when you will run this. And now the you have to create the reachability graph. Okay, so a reachability graph, you can see like uh, basically it contains nodes and transitions, and you could see this random slide which I was showing. Just that, let me get back to that random slide, this one. Okay, so the node will contain the distribution of all the tokens. So coming to this figure, so only two places were containing the token. So you can see the reachability graph. Uh, this only, the first state will only contains the token and two places, and then in the next state, this transition will be enabled because all its input place contains the number of tokens, and when it will be enabled, it will fire. When it will be enabled, then it will fire, and then uh, the, the token will be deposited. One token will be from at this place and one at this place. So basically, uh, why? Because the deposition of the token will be depending on the number of weight So this arc also contains weight 1 and this arc also contains weight 1. And then you can see uh, the places, sorry, the tokens from the places has been removed in the next state and it got deposited into the new places. And similarly, we can work out for every firing of the transitions. And this is the total state space. So it means these states are possible of, these are the only possible states of that system throughout the operational life. And just for the sake of the convenience, we have just written all these throughputs as lambda 1 up to lambda 12. That's it, nothing else, so that I can minimize the space to represent. And now this is the reachability graph creation. So you can see like this is M0, and after firing of TS0, it has led to this token distribution. And these are the number of places, and each place how many tokens basically it contains, and so on. And then during the random slide, we have already seen it can be transformed into the Markov chain. So you have to just replace each state with circle, and this is the Markov chain, and every transition contains the throughput. It means number of transitions per unit time, that is the transition rate. Okay. And this is a generator matrix. If you are able to recall, we have defined the generator matrix, which contains number of rows and columns. And because there are the total 10 states possible from M0 to M9, so just you can write it down from M0 to M9 in rows and columns. And then you have to fill in the elements. So, for example, you can see from M0 it is transiting to M1 with lambda 1. So you can see from M0 it is transiting to M1 with lambda 1. And uh, and the diagonal element, you could have seen one equation, diagonal element formula. Let me go back to that equation so that you could be able to recall. Yeah. So the diagonal element will be always minus, and you have to sum all the elements in that row. Okay. So this is what has been done here. So just a moment. Yeah. So minus, and you have to sum all these elements. So this is minus lambda 1. Similarly, from M1, let us see where all the transitions are there. So from M1, it is transiting to M2 as well as M4 with lambda 3 and lambda 11 respectively. So it is transiting to M2 with lambda 3 and M4 to lambda 1. And diagonal elements you can keep minus lambda 3 minus sum of all the rest of the elements. So that is why minus lambda 3 minus lambda 1 and so on. Okay. And you all already know like all these values of the throughput, which we have already computed here in this slide. So you have to just put those values and solve, and this will give the generator matrix, that is transition rate matrix. And now you have to compute the transition probability, like from what is the probability of transiting from one state to another state. So the funda is very simple. Suppose you want to transit from state to I to J, and you want to quantify the transition probability from state I to J. It will be, the transition rate from I to J, and you have to normalize this transition rate. So for normalization, you have to sum all the transition rates except the self transition. And this is done when j is not equal to I, otherwise it will be 0. So this will be the transition probability matrix. Okay. And now, beautifully, we can use those two equations. Let me go back to those two equations. Yeah. So this is sum of all the state probabilities will be equal to 1. That is M0 to plus M1 up to M9. And this is what we have written here. Here. So this is the steady state. Suppose M0 to M9, and this will be equal to this, and you have to multiply it by transition probability matrix. So by solving this, so all M0 plus M1 plus up to M9 is equal to 1, and solving this equation through analytical methods like Monte Carlo methods and all, you can get all the values of M0 to M9, which is this, and these are the basically state probabilities. Okay, and now if you go back, so I have found out what is the probability of my system being in M0, being in M1, and so on. If you see, there are the two for failure states. One is M3 and M8 because it is leading from like the acknowledgement has not been sent successfully. The acknowledgement was unsuccessful here also and here also to M8. And so what you can do is you have to just add the these two M3 plus M8 state probabilities, which are the failure state probabilities, and you can subtract it by 1. Or otherwise, you have to add all the state probabilities leaving M3 and M8. Then it will give the state reliability of the system. Okay. So what you have done, you have just added M3 and M8 and you have subtracted by 1, and which has given the reliability of 0.99603, which is a very good reliability figure. That was the crux. The crux is we have seen like how we have quantified the reliability of the system, and we have seen our reliability prediction framework, which contains basically 3 phases. In the first phase, we have to model the system after understanding the specification or the requirements, model the system using the Petri net. We have already seen the working mechanism of the Petri net, and after that we have to create the reachability graph, and then we have to utilize the mathematical knowledge, and using that we can easily quantify the reliability of the communication protocol. So not only communication protocol, even you can quantify the system reliability, breaking in smaller chunks, and you can find out the reliability of different subcomponents, and you can see how those subcomponents are arranged, whether in series or in parallel and all. And you can then apply the series and parallel reliability formula or reliability block diagram kind of, so that you can quantify the reliability of the overall system. So that was the crux of my session. In case of any doubts, I'll be happy to answer.
Participant, if you have any question, please either you can write it on the chat box or you can raise your hand. I can unmute you.
Participants, please, if any question, they may raise their hand, so we will unmute him or her. Sir, please unshare your screen.
Pardon?
Unshare your screen.
Yeah. Okay,
Okay.
let me unshare. Yeah.
Participants, please, if any question, they may ask.
Okay.
Sir, I have one question.
Yeah, please.
Sir, how will means this communication and all this affected by the stochasticity?
Okay. See,
Means you have talked about Markov chain and all this. So white noise is actually in relation with Markov process.
Relation of Markov process with
White noise process.
noise.
Noise process. If
See,
we
Markov, okay, as I said, the Markov process is basically works on the state space. So what basically Markov does, if you do have any system, you can break it down or you can decompose into the various states. And when any malfunction will happen, states will be deteriorated. Okay,
yes,
and that deterioration basically will get captured into the Markov chain. So, for example, if in communication some attack has happened, and those attacks will, jeopardize the state. So you can define the new state, like you can categorize your kind of attacks, and you can define multiple states, and you can see like if that state happens, then if there's a probability of the system reaching to that particular state, definitely the reliability of the overall communication protocol will be jeopardized, right? So in that way, any non behavioral states or non demanding states, if your system is reaching, your reliability will start compromising.
okay. Sir, in chat box there is one question.
Mhm.
Which are the different tools available for checking reliability of communication protocol?
Mhm. See, if you see the reliability of the communication protocol, you can only see the functionality. There are the various, tools, for example, T-type connectors or B2, BNC type of connectors. If you see, like, there are the various tools we can see, like, okay, the connectors are working very fine. For example, if you install the internet at your home, you have observed like, okay, there is a one tool who basically sees, okay, this cable is perfectly fine, and then he will install the connector. Or for example, in the TV, they do have one tool to see if the signals are coming. So there are the various tools, but I'm talking here about the quantification of the reliability. Quantification of the reliability means you have to, there should be some tool which can come out with the probability of the failure of a component. So you can see, they are the statistical methods, they are the statistical tools basically. Okay, so various models have been proposed where you observe the failure data, keep on observing the failure data, and you see the distribution of the failure data, what distribution that your failure data basically is following. And according to the distribution, you have to appropriately choose the right model. For example, if your distribution follows the failure, your failure follows the Weibull distribution, you have to choose the model which is based on the Weibull distribution, and inputting all the respective parameters, then you can quantify that. So the tools will be depending on the nature of your failure data, basically. If you are talking in terms of quantification of the reliability, whether it is a software reliability or it's a hardware reliability.
Sir, you have so delay timings in one
Delay.
table.
Yeah,
So
yeah.
what means, what is unit of that delay timings? Microsecond or second? Or
No, it was in second. It was in second. The
yes.
unit was right, right.
Okay.
So basically, the unit is you can define. I have used the TimeNet. There is a one tool, TimeNet, in which you can model this PetriNet. You can create a PetriNet model where you can define the time and the units also you can define. So there are other tools also like Petri or many open source tool also you can get, like how where you can construct a PetriNet model and you can run by inputting those the required parameters. And if you are dealing with the real time systems, because safety systems are generally real time in nature, it is very important to input the timing information, how much time it takes to transit from one process or one state to another state.
Okay, sir. Any participants have any question, they may ask, or they can write their question into chat box. Okay, sir, one group photo, please, with participants.
Sure, sure.
Please, participants, turn on your camera so we can take group photo with our expertise. I hope you all are present. Yes, all are present. Good news for us. Okay. Thank you.
Yeah, thank you so much, and
thank you, sir.
yeah,
Thank you very
for
much, sir.
accepting our invitation. Thank you, sir.